2021. So without further ado, Professor David Quere, please.
It's a real pleasure to be here. I thank the organizers for not only inviting me, but for organizing this very inspiring conference. Maybe I first apologize because we had extraordinary overviews from our colleagues, and so I chose a style which is a bit different, which is much more focused on something which is recent. So maybe this is my first excuse. My second one is the fact that I added to my original title a subtitle, which is from Mahadevan to Chandrasekhar, so it has obviously an Indian flavor. So these two distinguished, highly distinguished people did things which are not really related, and we can see this talk as something which makes a bridge between what they did. So I also thank Pascal Ossius, Yui Takai, Kexin Chao, and Oriane Huyghe Despointes. So these are the students who made experiments, the experiments that I'm going to show. By some kind of interesting coincidence, they are all women. Sluggish drops to start. So drops are sluggish. First experiment that we all know is you take an incline, so let's say plastic, you place a drop of water on this incline at a scale which is, let's say, 1 millimeter. The second one will be slightly larger. These are typical raindrops. They do not move. And so this, of course, is something which is visible with the naked eye, which is obvious in daily life. Even vertical window panes stick in a similar way drops. And the reason was discovered by someone who is nearly unknown, Agnes Pockels. So she was a German lady, and she was a sister of the distinguished Professor Pockels in Göttingen. And so she made a series of extraordinary experiments about capillarity at the beginning of the 20th century in her kitchen. Okay? And so she tried to publish, but she was unknown. She asked some help to her brother. He said, what you do is interesting, but I don't know where it could be published. So she wrote a letter to Lord Rayleigh. And Lord Rayleigh was working in the field, and he was amazed by the variety of discoveries she had done. And so he sent a letter to Nature, and he said, you should publish immediately this lady. And so Agnes Pockels, thanks to Rayleigh, is not completely unknown today. So in this experiment, with very good eyes, she saw something which is hardly visible, which is that these drops are asymmetric. So the front and the rear have different contact angles. And so she understood qualitatively that this asymmetry creates a force that opposes gravity. So drops are sluggish because they are adhesive. But they are also sluggish because if you make them large enough, and this is a real-time movie, they flow, but they flow at a velocity which is very, very low compared to what it should be on such an incline. So if you think of a river, for instance, a river is very quick, and the slope is much smaller, actually. Here, the speed was about 1 centimeter per second, which is a very low speed. And the reason is also related to what is called the contact line, the fact that you have a region close to the place where you have liquid air and solid, where you generate not only the pinning that we saw earlier, but some special friction, which was understood by Scriven about 50 years ago. So because of the contact line, drops have a high adhesion and they have a high friction. And so if you want to make them mobile, which is something we are looking for very, very often, in particular thinking of applications, you just try to get rid of contact lines. This is, of course, the easiest thing to think of. There are other possibilities, but this is a very natural one. And so if you get rid of contact lines, so if you somehow make the liquid levitate immediately, due to surface tension, it becomes very round, and you end up with an object which is more or less like that. And so this ideal object should have a very little adhesion, at least at a very naive point of view that we have here, and also a very little friction because it's exposed to a solid but very locally. So the first thing to notice is the fact that this is true if the scale of the drop is small enough, so smaller than something which is called the capillary length, above which gravity will anyway flatten the thing. But we will be constantly in this limit. So can you approach this ideal thing? By two ways. The first one is to have a solid which is very hydrophobic naturally, a mixture of chemical hydrophobicity plus texture at a small scale, invisible. And then you make an object which I'm going to call a pearl, which is indeed very close to the ideality we had in mind. And so when you look at that, you say, well, this object should be very mobile, and it is. The second way is to put the texture not on the solid but on the liquid itself. And so this is something you can achieve by little powder. So you have a powder, you put your liquid, your water on the powder, you shake a little bit, you coat the liquid, and then you can transfer this drop on any solid, or even on a liquid, actually. And so it's highly spherical because it does not touch the substrate. It is separated by this monolayer of powder. And then you can play with these little marbles, as kids can do. And they do not merge because they are self-protected. So it's difficult to make them merge. They are really isolated objects with very little interaction with the substrate. And as a consequence, we expect very little adhesion and very little friction. So this is exactly what I would like to discuss. What is the adhesion of these objects? I'll be quite quick on that. And what is the friction of these objects? And here I'll be more specific, and I will consider a limit, which I often said it's the most interesting limit, but I had not really worked on that, very little, and recently we did experiments on this limit. And maybe I say immediately, what is this limit? This limit is the one when the liquid is very viscous, okay? So we expect mobility, but it turns out that we have something that I could call mobility to the square when we go to a limit where mobility should be lower. And so this will be the main thing I will discuss, the fact that we somehow amplify the mobility despite the fact that we increase by a factor which I immediately say, which is 1,000, so it's a big difference, when we increase the viscosity. So adhesion first. So you remember the first thing, you place a drop on the plate, you tilt the plate until the drop departs. And so it's a given size, and you can, of course, vary this volume. And when you look at a pearl, you find that this angle at which the drop departs is, of course, a function of the volume. This is something you expect, because the heavier, the easier it is to move it. So this is very natural. It's a strong variation. It's nearly a hyperbola, okay? And, well, the reason is very clear. There is a little bit of pinning because there are some defects on the solid because there is a texture, and so you can pin the liquid. You can make that at quite quantitative, actually, and it's in itself, it's a very interesting question, which is, can you calculate alpha star? So this is something which can be done in a nearly quantitative fashion. It's one of the very few cases where you can really calculate this adhesion, which is, generally speaking, a very difficult question. Only thing to notice is the fact that because it's a very hydrophobic situation, these angles are very small, 5 degrees, 2 degrees, 1 degree, very different from what we are used to on the window pane, which can be 90 degrees and no movement, okay? And this is due to the fact that you reduce a lot surface area between the solid and the liquid. Now, if you take, instead of a pearl, marble, so you remember, now on a flat solid, but the surface is textured, you find something which is quite different. The first thing to notice is there is some adhesion. I said this liquid now is isolated by the powder, but however, you need a few degrees to move the thing. And this adhesion is independent of the volume, which is, of course, at first sight, a very unusual property. You would expect that heavier marbles go down more easily. So you can think of that a little bit. I will not go into the details of these things, but of course, the objects are a bit different. In the case of a pearl, you still have what is called the contact angle, or the complementary of the contact angle, which I call epsilon, to stress that it's a small quantity. And so you can, in particular, evaluate the contact between the solid and the substrate, the liquid and the substrate. Geometrically, this L is just the size of the drop times epsilon. And so indeed, if you make epsilon smaller and smaller, you decrease this contact, and you expect to decrease the adhesion, because the adhesion is fixed by this parameter. And so from that, you can balance the adhesion force and the weight, and you find a formula which tells you that alpha star should vary as 1 over the volume to the 2/3, which is nearly a hyperbola that we saw earlier. In the case of the marble, well, I'm really tempted to say that epsilon is 0. Okay? I'm tempted to say there is no contact, so there is no contact angle, and as a consequence, well, it's slightly different. However, we see a L. We see that there is a contact, and this was the first thing that was discussed by Mahadevan a few years ago. He said there is a contact even when epsilon is 0, because this drop has a little bit of weight. And so this weight tends to flatten the base, and it's a kind of critical phenomenon. Even if you flatten the base by a very small amount, or if you lower the center of gravity by a very small amount, geometrically, because it's a sphere, L is not negligible. Okay, and so saying that, you can calculate L, and you find that L is a highly sensitive function of R. Instead of being linear in R, as it is in wetting phenomena, it's quadratic in R. And so L square, which is the surface area of the contact, is L to the 4, and so this is highly nonlinear. And we'll see a very dramatic consequence of that in a few minutes. The second thing you can add is, well, what contacts the substrate is not a liquid, it's a solid, because it's a powder. And so you are tempted to say, I introduce a solid-solid friction, like for Leonardo was cited a few times, so let's quote Leonardo once again. You take a brick, you place on a plate, you tilt the plate, and you look at that. So it's a solid-solid friction, and if you do that, you immediately end up with the fact that alpha star should be independent of the volume. It should be fixed just by the friction coefficient that you have between these two solids, the powder and the substrate. So this is for adhesion. So we have a little bit of adhesion, and this adhesion is different in both cases. Now, what about the friction? So the friction is what we see when we are above the threshold of adhesion. So we can ignore now adhesion, and we look at the velocity for a given force, so for a given slope. And so if you take water first, well, on the inclined plate, a bit the same kind of tilt angle I had at the beginning, you see that it's so quick now that it does not stick first, and also it's so quick that I need a very high-speed camera to catch something, and this something is this drop, which is which we can guess that it's quick because we see the vibrations of it has, plus the fact that it takes the dust at the surface of the leaf. Here it's a lotus leaf, so it's another tribute to India. And so as a consequence, the rain cleans very nicely the leaf, what Bartlett called the lotus effect 25 years ago. If you follow the position of this drop as a function of time, you find that Z position is quadratic in time first, and this is a law of Galileo. So we have big names here, Leonardo, now Galileo, and it cannot be quicker. It's a law of free fall, okay? Of course, at the scale of a leaf, it can work, let's say 10 centimeters, 20 centimeters, but at the scale of a windshield, for instance, 1 meter, which is a vertical scale you have, it does not work anymore because your liquid reaches a constant velocity because there is some friction. And this is precisely what I would like to discuss. What is the nature of this friction? In the case of water, it's not simple. We tried a few ideas recently. I don't know if they are correct, but the main idea is to say, well, it's more or less the air which is around which fixes the friction. The solid has very little to do with that. Numbers, maybe. You see the scale is 1 meter, is 1 second, and so the typical scale for velocity in this example is 1 meter per second. So, of course, this is quite quick because the tilt angle is not very large. But I would like to discuss something where these mobility effects will be larger, at least in my opinion. So to see that, you do an experiment where you take two such objects, but the size is different, okay? So, and you place them on a tilted plate, and you look from above, okay? So it's a race. If you are interested in the Bible, it could be the race, the fight between David and Goliath, for instance. So my name being David, so of course I support as a winner the weak one, okay? And the weak one is a small one here. And so when I look at this race from above, I see that indeed, like it is written in the Bible, the little one is winning. And this is extremely unusual, and it's even more unusual in a viscous context, because when you are dealing with viscosity, you expect that the smaller the scale, the smaller the velocity, and even by a square. Okay, so here it's the contrary. When it's smaller, it's quicker. And this is something which tells you for the first time that indeed, when you go to the viscous limit, things are quite unusual. And this law was anticipated, was predicted by Mahadevan in a very famous paper, which is called Rolling Droplets. And he says the following. He says, when we are viscous, when the Reynolds number is smaller than unity, then it's not sliding, it's pure rolling. This is the first thing. And pure rolling has to do with viscosity, because you need Reynolds number to be smaller than unity. And it's a way of dissipating very little energy, because when it's rolling, the points are always at the same distance, and so there is no friction inside such a drop, except at the base. The base, which is this place here, the place L, okay? At the place L, you expect some dissipation. And so because it's a friction, you expect this dissipation to be sensitive to the square of L, and so this is the force power of R, and this is a way to make a long and subtle story very, very short. If you have a force power on the right hand of your equation and the third power, which is the weight, on the left hand, you expect that the velocity can be inversely proportional to the radius, which is exactly what you saw earlier. So it's a quantitative law. You expect that the velocity of descent is fixed by the viscosity, because you have viscous dissipation close to the L region, in the L region, but apart from that, there is no dissipation, and so as a consequence, smaller objects are quicker, something which is extremely unusual, in particular in a viscous context. There was a fabulous paper by Schnitzer recently where he took the Mahadevan argument, which is a scaling argument, and he made the complete calculation, which is a real tour de force. He worked on that 2 years. He's at Imperial College, and he produces even the coefficient in the Mahadevan law. So, small and viscous, you can use that. And so I cannot resist showing you one example in nature. So yeah, now I lost the control of everything. It's a natural example where you find the use of that. It's an insect which is called an aphid. So aphids are millimetric insects. This is the first thing to say. And they produce excrements which are highly viscous. And the name of these excrements is honeydew in English. And so honeydew is a very interesting word because it mixes honey, which is viscous, obviously, and dew, which is small size. Okay, so for these little bugs, they find ways to get rid of these excrements by coating them with a powder. And so it's very mobile because precisely it's a small marble. and it can be evacuated by any slope. So you are going to see this excrement which is coming. So it's not disgusting. You are going to see that it's just a little bowl. And the scale is interesting because the scale is about 100 micrometers. And so it's very viscous. You have to get rid of that. And so, well, the insect coats that with the powder, and then it's evacuated because you have always a little slope on the leaf where you find these insects. So I would like to do something now very innocent. I would like, because everything works nicely, so we have a law for this mobility, for the velocity that we get. It's a viscous law. So everything is linear in the viscous world. And indeed, the formula that we have is linear in all parameters. Linear in surface tension, linear in slope, which is in red here, alpha, linear in viscosity, and so on. So I'm going to consider a viscous liquid, glycerol, and I'm going to vary the slope. And of course, if I vary the slope, I increase more and more the driving force, which is gravity, and so I expect to increase more and more the velocity. So when you do that, you find that this is correct, but in a way which is not exactly expected. So this is the position of the liquid drop as a function of time, okay? And if the slope is modest, about 10 degrees, it's a linear thing, and the slope is the velocity, and the velocity corresponds to the formula we had earlier, okay? So this is the Mahadevan domain. However, when the slope becomes slightly larger, 20 degrees, which is not a big quantity, or even larger, suddenly there is a huge jump in velocity, or mean velocity, plus the fact that you have a very wavy pattern, as you can see. Okay, so this tells you that something else is acting to make the mobility of these viscous marbles or pearls much higher than the high value that we calculated. So this is what I call mobility to the square. Okay, it's a double effect, and so there is something to discuss here. Of course, I could directly extract from that the velocity now as a function of the slope. And this is velocity, mean velocity, as a function of the slope of the angle. And so at very low angles, 5, 10 degrees, you have the linear law which was predicted, expected from, for instance, Mahadevan model. However, you see a strong deviation. This is already a strong variation, plus a jump, okay? And suddenly you have a factor which is larger than 10. Okay, so your thing is moving at a velocity which you can see directly, which is half a meter per second in this case. And this velocity now is comparable to the viscosity of a drop of water. Okay, so you have multiplied the viscosity by 1,000, and the velocity is about the same, okay, roughly speaking. So this is amazing because it tells you that in this limit of non-wetting, you can drive very easily objects, which are liquid objects, but even better if they are viscous. Why is it like that? So you can have a look, of course, and so this is a high slope, 30 degrees, if I remember correctly, and you see the drop which is coming from the left, and the first thing which is visible is that this non-wetting drop is, I think it's visible, is growing with time, okay? It's growing with time, because when you increase the velocity, and because it's rotating, you increase centrifugation. Okay? And so you have a new force which is acting, and you have to take into account this force. And this is something which is very easy to do. This is the object. It has a size r, which now is not always constant. This can be growing as a function of time. And the way to understand that is just to compare the force that makes the object grow because of centrifugation with surface tension, which tends to make it globular. And this is a number, and this number is called the Weber number, so density times square of the velocity. And of course, when you change alpha, you change efficiently v, and because it's v squared, it would be a strong effect, times r, which itself can be a function of v, okay, which, as we understood. But you can measure this object, this quantity, of course, in all cases. And you can see whether the size is indeed a function of the Weber number, and the answer is extremely clear. When you plot the size of these drops as a function of the Weber number, so which you do from many slopes, you find that when the Weber number is smaller than unity, the size is constant, and this is the size of your drop. And when it is larger, there is a strong increase in the size by a factor which is, let's say, about 3. Okay? So 3 is not 10. Okay? It was even more than 10. So we do not explain everything by that, but we explain at least that, well, we have to take into account big changes in the shape of the drop. What can be these shapes? So the first one who discussed the shape of a revolving drop is Newton, and he said it should be slightly flattened at the poles and slightly inflated at the equator. Then came Laplace, and Laplace said, well, it could be something even more dramatic, which is a disk. And so this is the disk, the first one. Then came Rayleigh, and Rayleigh said, well, but because of this centrifugation, we could empty the center, and it could be a ring. And so the second object is the object of Rayleigh. And then Poincaré thought about that. He wrote a whole book about this question, and he said it should be more something like a peanut. Okay? So we have the donut from Rayleigh, we have the peanut from Poincaré, and so there was some confusion in the literature at that time. And so Chandrasekhar came, did a huge calculation. So a huge calculation by Chandrasekhar is maybe 2 pages of calculation, but for me it would be 60 pages of calculation. And at the end of the day, of this long day of calculation, you find that he found that the peanut should be more stable than the donut. Okay? So he showed that these two objects are natural when you think about rotation, but one is more stable than the other one. But we consider, we did not see peanuts here, so we consider only disk and donuts, because maybe you noticed that in the previous movie, at the end, there is something white that appears at the center. Here it comes, you see, it's white, okay? And so you see, indeed, a transformation between a disk of Laplace and a donut of Rayleigh. And so you can balance surface tension and centrifugation, and you find that there is a relationship between the size you observe, initial size, and this Weber number. And of course, when Weber number is 1 or smaller than 1, you just have R0, and if not, when Weber number is larger than 1, you have R larger than R0. And the two laws are not the same because the volume conservation is not the same.
Recording in progress.
Okay. Why not? So you can measure this size, and when you look at that, you find that successively, as a function of the velocity, indeed, you follow the scaling laws that we discussed. And so the object becomes larger and larger, and even much larger when you enter in the donut regime. So this is something that does not fully explain, except if you are very quick, but that does not fully explain the speed question. Why is it so quick? And so for that, you need to consider the friction. And the key thing is the friction takes place in the L region. This was the idea of Mahadevan. And we say, well, generally speaking, friction should be viscosity times velocity divided by size. Size can be now a function of the velocity. Interesting. It can be larger. So this quantity can be smaller. So friction can be smaller. So velocity can be larger. Good thing. But L, and there is a square, could be also a function of the velocity. And so this is the dominant effect. The reason is the following one. I do not enter the details, but you can calculate everything here. You say a drop is coming. It makes L, the L region. But this takes time. Okay? And if now it's rolling, well, it has to create always new L regions. And for that, it has a time which is typically L over V. Okay? So if you know the law of spreading L as a function of time, okay, then you inject this time here, and you find L as a function of V. Okay? And why is it so interesting to have a viscous liquid? Because a viscous liquid takes time to create L. It's slow. Okay? And so as a consequence, when you have these objects which are rotating, creating constantly new L, they do that slowly. So there is now a dynamic L, which is smaller than the static L, and so dissipation should be smaller. So it's just an extension of what we learned earlier, and you can calculate all of that, and you can find that L of V now has some different regimes which are there. So these are measurements, and you see that when V is small, so very small slopes, you reach a plateau. This is the Mahadevan regime, where the assumption was L is quasi-static. It is the one you observe when the drop is at rest. Then you have three successive regimes. One is the drop is still spherical, but it's rolling, and it creates constantly a new L, and it has no time to make the real L, the static one. And so you decrease L for that. Then you enter in a new geometry, so you have a new thing. And when you are in the ring domain, it turns out the calculation tells you that you reach a new plateau. But you see the variation of L is huge. It's between 1 and 1/3, let's say. So the square of that is a factor 10. And so you decrease the surface area, and so you increase the possibility of increasing your velocity by a factor 10, which is roughly what we saw earlier. So this is nearly the end. Just one little thing to add. We understand that it can be extremely quick. I did not really discuss the wavy thing, which is a nice pattern, and in particular because it's periodic, as you can see, at a very large scale. And the reason is what follows in the movie. So I stopped the movie when it was going down, tumbling down. But if I look slightly later, this is what we see. So we see now clearly the peanut, and then we see a transition, and then we see that we are going back to the initial thing, which is very slow, and it's reaccelerating, and so on. So I show it again. So you see, interestingly, the donut was very clear here. And because it's a soft donut, well, if you take a soft cylinder and you make it roll on the ground, itself takes off, okay? And so as soon as it takes off, it transforms its shape. If you have good eyes, you will see a very interesting object on the way, which is just here, 3 lobes, and then 2 lobes. And the 2 lobes, I alluded to that. This is the Poincaré peanut. Okay, and then you go back to the initial state, and you reaccelerate. So you have all kinds of transitions. So you explore all possible velocities that I described earlier. So in particular, this experiment tells you that, and you will not be surprised of that Chandrasekhar is correct, in the sense that between this peanut and this donut, once we leave the substrate, okay, which was a calculation of all the people previously, there was no substrate. They were thinking of celestial bodies. When you leave the substrate, then you have an irreversible transition between the initial donut, stabilized by the solid, and the Chandrasekhar Poincaré peanut. With that, I thank you very much for your attention.
Thank you, Professor David, for your wonderful talk and in sharing your insights. So now the floor is open to questions.
Yeah, thanks, David, for this very interesting talk. So I was wondering, in your model, you have this wetting length scale L. Wouldn't you actually need 2 length scales, one in flow direction or in the direction of droplet movement and the other perpendicular to that?
Yeah, so the idea is the same. So the L region is a region of contact, and it's also the vertical region on which we consider dissipation. So the dissipation takes place in a volume which is L cube, actually. So we need only 1 length scale, which is, of course, something very convenient.
Okay, thanks.
Okay, so David, I also, when I saw your movie and you said it's a donut, I said, no, he's not thinking correctly. That's the first order refraction Poisson point because you were backlighting. And then the last movie convinced me maybe it is a donut. But my suggestion is the following. If you do some ray tracing, then you'll find out why the first order refraction, the glare point will be the size, that'll be dependent on the numerical aperture of your camera. But it seems to be larger than that. And if you did some ray tracing, you'd find out the size of the hole.
Yeah,
the donut hole.
Yeah, so two things. So, of course, we were very interested in these shapes. And we did an experiment with, what is the name in English? So, a metal with a low melting point, okay?
A low melting point.
And so, the kind of thing which are kind of metal which is used for soldering, okay? And so then you make these kind of shapes, and at the end of the race, there is a bucket full with water, and so you solidify the thing, and you can see the object directly. So I think it's necessary to do that to be sure of what we do. By the way, when you do that, you generate very often these peanuts, okay? And they are very well known for people who are interested in celestial bodies. They are called tektites, okay? And so tektites are supposed to be made this way. Something is coming to the Earth, which is relatively big at the scale of 1 centimeter. It's in fusion, it's liquid because of course, the friction it had. And so it holds a little bit. And so as a consequence, it deforms in a way which is exactly this one. So we are quite confident that these are the objects I described. There is one, actually, you have very good eyes, so there is one thing which is not really true. These are not real donuts, in the sense that there is still a little layer of liquid inside. So it's on the way, but there is some nucleation here to create a real donut. So
but you should be able to get the size out of your movies.
Yeah, you can do that, yeah.
Yeah, very interesting. I have a question whether there could be a molecular timescale that plays a role, because ultimately, if it's a friction phenomenon, it'll be the interaction between your molecules and your interface, right? I mean, if it isn't the marble case, and if then your viscosity is very high, then you would have a long time to align to, let's say, a different environment because you are in the liquid to air regime. And then you have a very short contact time with your surface. And in that time, if it's too short and the viscous is too high, you should get less friction because everything doesn't align very well. But I have no idea for the numbers. Can this be achieved here?
Yeah, so you are pointing out the complexity of this curve in a sense. If I go back to this curve, we see a succession of dynamics actually. And so in particular, when we go to this, there is this, I don't know how to start, but maybe here. So at some point the velocity is small because I am contacting the solid, and so there is indeed a very long time scale then, and so this viscous dissipation is relatively high compared to what it will be. It's low in absolute value, but it's high compared to what it will be later. And so we see this acceleration due to this change of shape. Then we reach a maximum height where really the height is much higher than the slope is high, and so the velocity is very large because probably of what I said, the contact becomes extremely low. As you said, I maybe oversimplified the question because I always considered that it remains viscous, which is not completely obvious because when the object is large and quick, it could be the air which is around. When you put numbers in that, it seems to be correct, okay? So what you said is that the detail is a bit complicated indeed, but I think that it seems that everything can be put together as I did.
Thanks a lot for the interesting talk. I had a question regarding the particles. So these droplets, when they slide down the surface, they experience high deformations. And depending on the particles, they may cause the liquid to show some non-Newtonian behavior. Have you considered that? So, for example, for spreading droplets, it's been shown that one of the explanations could be, so highly viscous liquids which show shear-thinning behavior, but when spreading, they are as fast as water, for example, whereas their zero shear rate viscosity is like 100 times water. And one explanation is that there is a thin lubricating film because the fluid has shear strength. Do you have any comment regarding that?
Yeah, so of course we can think, there are two little things to say about what you said. So I use glycerol here. So glycerol, I'm very confident that at the shear rates that I used it remains Newtonian. And this is a very important point. I should have said that. It's a simple liquid. But in your question, there is something which is very relevant, which is to say in complex fluids at large, very often are highly viscous, but they are also at the same time non-Newtonian. And so how would we behave in something like that? Do they behave as a solid or do they behave as a liquid? Well, there are many possibilities. And so this is precisely what we are studying at the moment. How can we control the speed of very non-Newtonian fluids? And I hope I can give you an answer in a moment. But for what I presented here, I'm very confident that it's always Newtonian.
Okay, thank you.
Thank you for your questions. Now, for the interest of time, conclude the talk. So once again, please give a round of applause to Professor David. And you have a small token of appreciation also.
Okay, so Nandi.